Consider two set associative cache memory architecture WBC, which uses the write back policy, and WTC, which uses the write through policy. Okay, there are two policy: write block policy, write back policy, and write through policy. Both of them uses the LRU. LRU means least recently used policy. In this, whichever will not be used much often, that will be removed at first. The cache memory is connected to the main memory. Which of the following statement is true? Cache is connected to main memory. Okay. A read miss in WBC never evicts a dirty block. Dirty block means what? If there is some another memory location is accessed in the cache, then it will change that block. So it will be a dirty block because a dirty bit is assigned if there is any update inside the cache memory. So it is telling it will never evict a dirty block. So it's not possible because inside the cache memory, uh, we can decide now. Okay, that means we have to access that data from another memory location or from that memory location. That means if the data is not inside the cache, so we have to add the data inside cache memory. Okay, and if that data is useful, then we will add from another cache memory, and if it's not useful, then we will not use, then we will not add. So it's upon our decision. That means we might decide not to add it because the data is already inside the cache from another memory location, which is more useful. Okay, so there can be a dirty block in the case of a read miss in WBC. So this statement is false. A read miss in WTC never triggers a write back operation of a cache block to main memory. A read miss in WTC. See, this statement is true because what happens? This is write through policy. So data is always kept synchronized in write through policy. In that case, we never need to perform a write back operation to remove any entry from the cache. Okay, but it is telling now what read miss in WTC never triggers a write back operation. So this will be always true because if in the case of WTC, data will be always synchronized, so we don't have to perform write back. Okay, never we will have to perform the write back to remove any entry from the cache because data is already synchronized inside the cache memory. Okay, so this statement is true. Third option, a write hit in WBC can modify the value of the dirty bit of a cache block. See, this statement is also true. A write hit in WBC can modify the value of the dirty block inside the cache memory. See what happens if there is a write hit in WBC, it means we are writing directly into the cache. Okay, so in that case, this will also change the dirty bit. So this statement is also true. A write miss in WTC always writes the victim cache to main memory before loading the missed block to the cache. So what it is telling, write miss in WTC always writes the victim cache block to main memory before loading the missed block to the cache. See, there are two type of blocks here mentioned: victim cache block and missed block. Okay, so mixed block is one we want to access. Okay, and the while victim block, this will be replaced by LRU. Okay, So when there is write miss in WTC, it means the data we are trying to write is not inside the cache. So now we will want to load into the cache, or we will or we may not want to load inside the cache. Suppose if we don't want to bring it into the cache, in that case we can directly modify the main memory. Okay, so in this case this statement is false, because it depends we want to load inside the cache or not, because we have to modify the main memory now. So, and let's consider if we decide to bring inside the cache, then we may or may not need to replace the victim block, depending upon cache block is full or not. Okay, so this always writes the victim cache block to main memory before loading the missed block to the cache. This statement is false. So only true statement are B and C. Okay, see next question. Consider a hard disk of 512 GB with 32 storage surfaces. There are 4096 sectors per track, and each sector holds 1024 bytes of data. The number of cylinders in hard disk. So what is hard disk capacity? Hard disk capacity 512 GB. If it converted, this will be 2 to the power 39 byte. Okay, so and number of surfaces is 32. There are 4096 sectors per track, and each sector holds 1024 bytes of data. So for each track I will find out uh, see, there are 4096 sectors. So what is at first disk capacity? Because disk capacity has been given here 512 GB, and this will be equal to number of surfaces into number of tracks per surface into number of sectors per track into number of bytes per sector. So just we have to equate 2 to the power 39. This will be equal to number of surfaces we have to find out. What number of surfaces is given? Number of tracks is not given. See, number of tracks is not mentioned. Number of, this is sectors per track. Okay, so in this case number of surfaces is 2 to the power 5 into number of surfaces is 2 to the power 5 into number of tracks per surfaces. Let's consider this one, x, into number of sectors per track. This is 4096. This will be 14 or 12 into number of bytes. This is to the power 10. So if we equate, this will be 22 plus 5 27, and 27 39 minus 27 12. So x will be 2 to the power 12. This will be 4096. So this is the value of x, 4096. So this is the number of cylinders also. Okay, number of tracks per surface edge, so that is the number of cylinder. Okay, see next question. Number 55, the baseline execution time of a program on 2 gigahertz single core machine is 100 nanosecond. The code corresponding to 90% of the execution time can be fully parallelized. The overhead for using an additional core is 10 nanosecond when running on a multi-core system. Assume that all cores in the multi-core system run their share of the parallelized code for an equal amount of time. The number of cores that minimize the execution time of the program. So see here what has been given. Here baseline execution time is 100 nanosecond, and program that can be parallelized is 90%. That can be parallelized is 90%. That means 90 nanosecond can be parallelized. Okay, 90 nanosecond program. Overhead cost of additional core is 10 nanosecond. Overhead cost 10 nanosecond. Okay, so we have to find out the execution time for n core, because here number of cores has been not given now. So I will take n number of cores. Okay, now see execution time for n core. This will be equal to parallelized time divided by n. So what is parallelized time here? 100 nanosecond plus fixed time plus overhead time into n minus 1. So now find out this one. So what has been given, we have to minimize the execution time now. So at first find out the execution time. Let's consider this is Tn equal to parallelized time 100 divided by n. Fixed time is 90 nanosecond can be parallelized. So fixed time is only 10 nanosecond plus overhead is 10 into n minus 1. Just see, solve now this one. So Tn is equal to here. Okay, sorry. Parallelized time is here 90 now, not 100. This is 90 because 90% can be only parallelized. So 90 by n plus fixed time is 10 plus overhead is 10 into n minus 1. From where we can solve this one? This is 10 n minus 1 and 10 n minus 10. So this will be cancelled. So this will be 90 by n plus 10n. We have to minimize this one, so we can use a differentiation dtn by dn. This will be minus 90 by n square plus 10. If we put equal to 0, so n square will be what? 90 by 10, 9, n equal to 3. This is simple execution, you can solve this one. Okay, so this will be the number of cores. So what we have done here? Here baseline execution time has been given 100 nanosecond and parallelized time has been given 90%, so 90 nanosecond, and fixed time will be 10 nanosecond, and overhead cost has been given 10 nanosecond, and number of multi-core system. So we have to find out the number of core because this is running on multi-core system. So we will find out the execution time. So parallelized time, see, execution time for n core, parallelized time in means what? All the cores will be executed simultaneously. Okay, so we have to divide by n. See, what is this one? The number of cores that will minimize the execution time of the program. So execution time of n core will be parallelized time divided by n plus this is the fixed time, and overhead. See, overhead will be what for remaining n minus 1 core, because first core will be required for all, but for remaining n 10 nanosecond is only required, because see, this part will be for first core and remaining 10 n minus 1. See, till here we are, sorry, if we take na parallelized time plus fixed time, actually this is from here na, 1 second. Our formula is this one, like this. Okay, so parallelized time divided by n plus fixed time, this is for one core, and remaining for n minus 1, this will be overhead time. This is for n minus 1 core and this will be for 1 core. Now see this question number 56. A given program has 25% load store instruction. Suppose the ideal CPI cycles per instruction without any memory stalls is 2. The program executes 2% miss rate on instruction cache and 8% miss rate on data cache. The miss penalty is 100 cycles. The speed up rounded up to 2 decimal places achieved with the perfect cache, that is with no data or instruction cache miss. Okay, see. Here number of instruction has not been given, so I will consider, let's, sorry, let's number of instructions equal to 100. Okay, there are 100 instructions. So we have to fetch 100 fetch and 100 for 100 instructions. And this will come from instruction cache. And 25%, that is 25% instructions are data fetch. That means store instructions come from data cache. Here see, 25% load store instructions. 25%, that means 25 instructions are data fetch or a store instruction. Here are given a load a store instruction. So 25 instruction are load a store instruction, and this will come from cache. So in total 100 fetches, we will have 2% miss ratio. 2% miss, and each miss penalty is 100 cycles. So in 100 fetch, 2% miss rate. So 2 message, and this will be 200 cycles penalty. Okay, and from data stream 8% miss cache from data stream. So for the data stream 8%, that is 2 message, so 200 cycles penalty. And from data fetch, so see 25 instruction are data fetch. So 25 8%. This will be 2 now. So here 2 miss will be for data cache. So here also 200 cycles penalty. Okay. So total cycles taken to execute 100 instruction will be what? Suppose the ideal CPI without any memory stalls is 2. So ideal CPI is 2. So for 100 instructions, for 100 instructions, total number of cycles, let's see this page. For 100 instructions, total number of cycles will be, there is ideal CPI 2 now. So for 100 instruction, it will be 2 plus, there is penalty also, 200 penalty for cycles fetch, 100 instruction fetch, and for 25% 200 penalty will be also. So total 600 cycles. So its CPI will be 600 by 100 for 100 instructions, 600 cycles. So, and in the case of perfect caching solution, what we will have to do? We have zero miss. In perfect caching solution, there will be zero miss. Hence, the CPI will be, if we remove the miss, then what will be its CPI? 2. See, if there is no miss, then in that case, what? We will remove these parts. Simply, there has been given in the perfect, there is only 2 memory. There is only 2 cycles per, sorry, here it has been given for ideal case CPI is 2. So a speed up will be what? Here total CPI what we have calculated, 6 divided by ideal CPI is 2. So a speed up will be 3. Okay. What we have done here, I have just considered 100 instructions, and there are 25% load store instructions. So for 25% data fetch will be there. That means for 25 instructions, and 2% miss rate is there no on instruction cache, and 8% miss rate on data cache. So 2% miss rate on instructions. So for 100 instructions there will be 2 misses and total 200 cycles penalty, and 8% miss rate on data cache. So data fetch is 25 instructions. So for 25, 8% will be 2 misses. So for 2 miss there will be 200 cycles penalty. So total number of cycles will be for 100 instructions plus miss penalty. So 200 plus 200 plus 200, total will be 600 cycles. So CPI will be 6. So speed up will be ideal total CPI divided by ideal CPI. So 6 by 2 is equal to 3. Question number 57. Consider the following code a snippet using the fork and wait system calls. Assume that the code compiles and runs correctly, and the system calls run successfully without any errors. So this is the code, int x equal to 3 while x is greater than 0, fork, okay, print hello, wait null, x minus minus. So how many times this loop will go? We are decreasing the value of x each time inside while loop. So 3, 2, 1. 3 times this loop will go, and each time fork is calling. So total number of times the printf statement is executed. Okay. It is asking the number of times printf statement will be executed. So see, if x equal to at first 3, For call will be there and printed will be there. Fork and print. X equal to 2, fork and print. X equal to 1, fork and print. X equal to 3 and fork is called, then the number of child process will be, this will be 2 to the power 3. Okay, x equal to 2, in this case number of child process will be 2 to the power 2. In this case x equal to 1, in this case child process will be 2 to the power 1. So here 8 plus 4 plus 2, total 14. So 14 times this will printed hello. Okay, because here now fork is in itself is a still a system call. Okay, so in each time fork will be called, total number of child process, each time this printed hello will be printed. So just calculate the number of childs created, to the power 3 plus to the power 2 plus to the power 1. So total this will be 14. So this is simple question. So see this question, consider the entries shown below in the forwarding table of an IP router. Each entry consists of an IP prefix and corresponding next hop router for packets whose destination IP addresses match at the prefix. The notion n, this is the subnet mask now. Most significant n bits set to 1. Okay. So this is prefix and next hop router has been given. This router forwards 20 packets each to 5 hosts. Okay. The IP addresses of the hosts are 5 host IP address has been given. The number of packets forwarded via the next hop router are 2. So this is the forwarding table. Okay. So 5 IP has been given. If we just find out in its octet format, in binary format, value its value 10.1.1 point, because see 3 octet are same now for all. 1 2 3 4 5 6 7 8. This is also 10.1.1 128. So 1 2 3 4 5 6 7. This is 64. 10.1.1 64. 1 2 3 4 5 6. This is 192. 10.1.1 128 plus 64. 1 2 3 4 5 6. Okay, so this is 5 IP has been given for each hop router, and here IP 10.1.1.6, 10.1.1.72, 10.1.1.132, 10.1.1.191, and 10.1.1.205. Just find out its binary value for last octet. This will be 10.1.1.16, 128, 64, 32. This will be 16, 41, 4, 40, 1, 2, 3, 4, 72, 10.1.1. This is 128, 64 can be added. Yes, 64 plus 8 no, so 8. This is 32, 8. This is 64, 3 5 8, 3 4 5 6. That's fine. 1632. 10.1.1 128 plus 4. So 64 32 16 8 4. This is 10.1.1 91 128 plus 64. This will be 192. So this will not be, and 33. All 1 2 3 4 5 6. This will be 33, no? 336. Hmm. This is 10.1.1.205, 128 plus 64, 192. 32 can't add. 192 plus 16, 8. So we can't add 16 also. 192 plus 8, 200 plus 4, 204, 200. So this is its corresponding IP address. So see from which one this is matching more. This IP address, first one, from which hop router it is matching maximum. At first see whatever is matching there, no? So this is matching with R3 maximum. Let's see R3, this one 0101. This one is matching with R4 maximum. 10, this is R2, this is also R2, and this is R1. Okay, so maximum matching is with all this IP addresses. So from here longest prefix matching we can get what is longest prefix matching here? This one, no? See here how many prefix matching is there? Only 3, because say 30, 30. Remaining are matching. I am just calculating here. You can see that one. This one R3, how many matching? Only 2. This one, how many matching with R2? Till here, no? 5. This one, how many matching? R2, 2 only. And this one, 1, 1, 4 only. So maximum matching is this one. This one is maximum matching, no? What is 132? The number of packets forwarding via the next hop router R2. So 5 and this one now 132 and 191 are the IP visiting from router R2. Okay. Router forwards the router forwards 20 packets each to 5 hosts. So for R from R2 router there are 2 IP addresses now forwarding. So for 5 hosts from R2 there will be 2 into 20 packets, that means 40 packets will be forwarded. So we have to just find out from R2 router how many packets will be forwarded. Okay, see this question 59. Let G be sigma sp, the context free grammar in Chomsky normal form. Here terminals are ABC and B containing 10 variable symbols including the start symbol. The string W A30 B30 C30 is derivable from S. The number of steps in the derivation is to whole W star. Okay, so for in CNF, for this is Chomsky normal form now. So number of steps will be what 2 to the power 2 into length of this word minus 1. So what is the length of this word? 90. So 2 into 90 minus 1, this will be 179. Actually this is simple question. 179 will be answer. See question number 60. The number of edges present in the forest generated by DFS traversal of an undirected graph G with 100 vertices is 40. 100 vertices and the number of edges present in the forest generated. So this is vertices and this is 40 edge. The number of connected components in G. So we have to find out the number of connected components. So what is connected components? This will be the number of connected components in the forest generated by DFS traversal. So forest have 100 vertices. So see, if there is 100 vertices and 0 edge, the number of connected components will be 100. And if we add one edge, so it will reduce the number of components by 1. Additional edge will connect 2 components. Okay, and we have to find out, we have to create only forest, not a cycle. So we can add the edge between different what component only, because if we add the edge in the same component, then it will form a cycle. So repeatedly one edge 40 times we have to add now. So this is simple. See, if we add 100 vertices and one edge will be there, so what will be happen here? Here will be 99 components. Just the example, no? 4, 6. 6 edges are there. There are now 6 component. Sorry, 6 vertices are there. So 6 component. If we add 2 vertices, then how many components are there? 1, 2, 3, 4, 5. 6 vertices, 1 edge. The number of components is 5 components. In the same way, if there are 100 vertices, 40 edge, the number of components will be 100 minus 40. There will be 60 components. Okay. Question number 61. Consider the following two regular expressions over the alphabet 0, 1. So here alphabets are 0, 1. Here two strings, two regular expression is there. 0 star plus 1 star. That means here 0 can be a limited number of times and 1 can be 0 or 1. Okay. And here 0, 1 star plus 1, 0 star. Here this will start with 0 and 1 can be unlimited number of times, or 1 it will start with 1 and 0 can be unlimited number of times. So two regular expressions are there. So this is completely 0 or completely 1, and empty string can be also there including null. And this one 0 followed by 1 or 1 followed by 0, there can't be empty string, no? So we have to, what we have to do, we have to find out the length or equal to 5. So 0 and is less than or equal to 5. Any the number of strings I have taken. Sorry. So number of strings can be from 0 to 5. Okay. So total number of such strings can be, there are two alphabets, no? So 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, this will, it will go 2 to the power 4 plus 2 to the power 5, this will be 2 to the power 6 minus 1, so 63. But here this will be total number of strings, but here only given two regular expression. From two regular expression only we have to find out. Okay. So see, for first string this is r equal to 0 star plus 1 star. If we find out how many are there of length from 0 to 5, what can be null? Uh, from 0 at first 1 0 2 0 3 0 40 or 50. So total how many strings? 1 2 3 4 5 6. 6 strings. In the same way for 1 there will be also 6 strings, but 1 we have also taken a null. So in this case there will be total 12 minus 1, that means 11 strings. Okay, next is second string is 1 0 star plus 0 1 star. Okay, so at first say 1 0 star of 5 length. 0 can't be possible, no? 0 length, so 1 can be there. 1 0 1 double 0 1 triple 0 or 1 4 0. How many? 3 to 5. In the same way 0 1 will be also 5. So total here 10 strings. um, See, is there some common strings in both? uh, Here 1 and 0 are common now, because see, this 1 will come in first expression also, and for second 0 0 1, like this will be 0 1 1, there 0 will come. So 2 are becoming common in both, so 2 we will have to subtract. So R union is, if we find out total number of strings in R, there are total 11, here total 10 minus 2, because 1 and 0 are already taken in 11. So this will be 11 plus 8, 19. Okay. Here which, what is the question, which are neither in R nor in S. So total is 63 minus 19. This will be how much? 44. Okay. So we have to just check how many strings it is generating. Question number 62. Consider a memory management system that uses a page size of 2 KB. Assume that both the physical and virtual addresses start from 0. Assume that pages 0, 1, 2, and 3 are stored in the page frames 1, 3, 2, and 0 respectively. The physical address corresponding to the virtual address 2500. Okay, at first see what has been given. Page size 2 KB. This will be 2 to the power 11 byte. Virtual address, both the physical and virtual address start from 0. Here virtual address has been given 2500. This is in decimal, no? If we convert this one in binary, I will convert in binary. 2500 binary, how much will be there? It's better convert in what, in 16 format, no? Even convert, okay, no issue. 2 be divide, no? 0, this will be 1250. This will be 6250 1 312 0 156 0 78 0 39 1 19 1 9 1 4 0 2 0 1. So its binary is what? 000111 000 100. Okay. 11 byte. How much byte is there? 3 3 6 3 9 3 12. So page size is of 11 byte. So offset will be of this 11 byte. This will be 11 bit offset, and 1 bit this will be page number. Okay. Assume that both the physical and virtual addresses start from 0, assuming that the page 0, 1, 2, and 3 are stored in the page frames 1, 3, 2, and 0 respectively. Okay. 1 is stored in 3. See? Okay. So page number is 1 is stored in. This is page number 1. So page number 1 is stored in page frame 3. So its physical address will be offset will be same 0 0 1 triple 1 triple 0 100, and its frame number this is 3, and this is offset. So we have to calculate the physical address. So this is physical address, just find out in binary value it's. So what will its binary value? Till here it was 2500. So we can directly calculate how many zeros are there. 11, no? So this value will be 2 to the power 12. So its decimal address will be 2 to the power 12 plus 2500. So 2 to the power 12 is 4096 plus 2500, 6956596. So its address will be 6596. Number 63. A bag contains 10 red balls and 15 blue balls. Two balls are drawn randomly without replacement. Given that the first ball drawn is red, first is red, the probability rounded up to 3 decimal places that the both balls drawn are red. So here 10 red balls and 15 blue balls. So what we have to find out, given that the first ball is red, the probability that the both balls are red. Two balls are drawn randomly. So how many red balls are remaining? One red ball is already taken. So 9 red balls are still there, and total we have to find out from 9 plus 15 red balls. So this is simple. 9 by 24. This will be what its value 0.375. See this question. Consider a digital logic circuit consisting of 3 2 into 1 multiplexer M1, M2 and M3 as shown below. X1 and X2 are input of M1. This one M1. X3 and X4 are input to M2, and this is M3. ABC are select lines of M1 and M2 and M3 respectively. ABC select lines. Okay. For an instance of inputs x equal to 1, x2 equal to 1, x3 equal to 0, and x4 equal to 0, the number of combinations of ABC that give the output y equal to 1. The number of combinations of ABC that gives the output y equal to 1. Y is what? This one now. We have to find out at first the value of y. So ABC, let's see this one D, E, okay. So what is the value of D? A complement x1 plus ax2, and x1, x2 value has been given. So x1 is 0. Okay, here value is given here, no? X1 equal to 1, x2 equal to 2, x3 equal to 0, x4 equal to 0. So x1 equal to 1, so this will be a complement. X2 equal to 1 plus a, so this will be 1. E value, this will be b complement x3 plus bx4. X3 equal to 0, so this is 0 plus 0, this is 0, total 0. So y will be what? D1, this is 0. Simply C complement. Uh, See, y equal to C complement, okay? So we have to find out the combination of A, B and C. So just make a truth table, no? It. So y complement is our answer, no? I need only that combination. So how many combinations are there? 4 only. The number of combinations A, B, C that give the output 1. Oh, simply y. C. C complement. So C complement is how many? 1, 2, 3, 4. So this will be 4. See question number 65. Consider sending an IP datagram of size 1420 bytes, including 20 bytes of IP header, from a sender to a receiver over a path of 2 links with a router between them. The first link, sender to router, has a MTU maximum transmission unit of size 542 bytes, while the second link, router to receiver, has a MTU size of 360 bytes. The number of fragments that would be delivered at the receiver. So IP datagram of size 1420 bytes we have to send, and MTU size is 542 bytes. So maximum transmission unit. So this is sender and this is receiver, and here MTU has been given 542 bytes. The first link, sender, has the MTU 542 bytes. The second link, router to receiver, here we want to see router, okay, this has MTU of 360 bytes. The number of fragments that would be delivered at the receiver. So here data will be what? 20 byte is header, so maximum data 522 bytes. Here maximum data 340 byte. Maximum MTU, this is 522 byte. But this is not the multiple of 8. So if we consider in the multiple of 8, 648, 42, 42. So we have to subtract 2. So this will be 520 byte. And this will be 348, 4. We have to subtract 336 byte. Okay. So fragmentation of 1420 20 bytes including 20 byte of header, so 1400 byte is data there. So I think 3 fragment na, 520 plus 520 plus how much will be left? If 1400 is the fragment datagram, so 520 plus 520 plus how much is left? 1040, 1400, 360, and each will be added with 20 byte of header. So 3 packets are there, and from this one receiver we will have to manage. So see here, first 20, 520 we are sending to receiver, and receiver MTU is 336, 336 and 20 bit is of header size. So how much is left? 4, 8, 184, and this will be 20. So 1, 2, again 25, 20. This will be 2336 and 2184. 3, 4, and last one 360, 20. So 2336 and 20, how much it will be? 24. So 5 and 6. So total 6 fragment will be there now. So what we have done there? Sender M2 size is 542 bytes and receiver M2 size is 360 bytes. It's given an IP datagram of size 1420 bytes. So and 20 byte is already in the header size. So 1400 byte is the datagram. So we have found out the MTU of sender. Here also 20 byte of header is included. Not included, we have to include later. Okay. So M2 size is 542 byte, but 20 byte data we have to include. So its M2 will be 522. But this should be in the fragments offset. It should be in the multiple of 8. So we have calculated in 520 only. Okay. So 1400 will be divided in 520, 520 and 360. And in that case, in receiver, it will be again divided. 520 will be divided in 2 bytes, 2 fragments, 336 and 184. So total like this, there will be 6 fragments.